Hi, I'm Alan Ross, and this is a power panel. We're doing a power panel on something that most people don't think has changed in 100 years, but it's cables, innovations, applications, and testing. I want to thank our guests. Bob, thank you for joining us. Ben, thank you for joining us. And Dr. Yingli, thank you for joining us. We're going to have a lively discussion because Ben is actually going to co-host this with me. I'm the moderator. I am the managing editor of APC Media's two major brands, Transformer Technology and Power Systems Technology. This falls under the Power Systems Technology area. So I'm looking forward to this. Let's hear a little bit about you all. So, Bob, just talk a little bit about your background, your company.
Good afternoon, Alan. My name's Bob Hobson. Been in the power industry for 40 years. Mostly in high voltage, a good amount in previous times working on medium voltage. I've worked across the whole industry from utilities through cable manufacturers. I have expertise in AC and DC, 525 kV, AC up to 400 kV. I do a lot of ampacity calculations today, and I'm experienced in the utility, the manufacturing, and the consulting side. I'm working on a very large distribution system upgrade right now, doubling its capacity. The company I work for, Burns & McDonnell, we've been around since 1898. It's 100% employee-owned. We're one of the top 5 AEC firms for safety. Very strong ownership mentality helps us push the technology, and we're always looking to do things better. We actively support community initiatives, including STEM, mentorship, and our primary focus is our customer success. We hope to make sure that everything we do makes them successful, and in turn, that turns around and makes us successful.
Excuse me. I know Burns & Mac is a leader in the industry and what you do, so I'm interested about the project that you're working on, but I'm sure Ben will bring that out. Mr. Lanz, if you'd talk a little bit about yourself.
Sure. So I've been in the industry for a little over 30 years. Most of that has been in the area of cables, reliability, diagnostics, but in asset management in general. Over the years, I've been involved in the development of diagnostics, in the formation of working groups and leadership of different industry guides and standards. IEEE, actually all of us three have been involved in ICC, especially Yingli Wen will be talking about her leadership at ICC, but also been involved in organizations such as Power Delivery Intelligence Initiative, which is an organization that promotes best practices in T&D grid infrastructure investment. And most recently with Osmose, helped start a company a number of years ago, ImCorp, that was acquired by Osmose. And now Osmose is a company that's been around for over 90 years, most known for our work in the area of wood poles and supporting utilities. But our services have expanded over the last couple decades into all different assets. So we have the expertise, the diagnostic technologies, and the knowledge of how to implement solutions, cost-effective, capitalized solutions to address the aging infrastructure of our nation and around the world. And we actually are focused on that area of solutioning for extending the life of assets. And of course, today we'll be talking about cable.
Good. Dr. Yingli Wen, if you would talk a little bit about yourself and your company.
Good afternoon. My name is Yingli Wen. I'm currently working with Edison. I have been with Edison for nearly 25 years and I have been in the power industry for over 30 years. My experience with Con Edison mostly in the testing and diagnostics of distribution cable and accessories. I'm currently the one of the key members in a project that work on a smart monitoring for the underground distribution network system. Before joining Con Edison, I have been with Pirelli Cables, North America, and now many of you know as Prismium. I have been working, when I was in Pirelli, I work heavily with G retardant XLP insulation, which is a new type of G retardant XLP insulation from the normal XLP, TR XLP insulation we use in North America. So I think it was trademarked PTR. Many of you probably know about it. And I also participated in the reduced wall EPR cable, which became the base of ICA or AEIC standard on reduced diameter cable specification. So I have my PhD in electrical engineering from the University of Connecticut. I was the ICC chair. Ben mentioned ICC. I was the chair from 2022 to 23, and now I'm still participate in the executive committee of ICC. About Con Edison, the company had company's history goes back to 1823 when it was New York Gas Light Company. So even though many utility companies have the name Edison in it, I would say Con Edison is the only company that can say to have a very strong association with Thomas Edison. Very proud of that. So we have the largest underground distribution system in at least in North America, if not in the world. And so our distribution system covers over 600 square miles, and the underground network system includes more than 25,000 conduit miles and more than 97,000 miles of underground cables.
Amazing, amazing. So I just have to say, who was this guy Edison that you all are named after, right? It's quite a pedigree to have Edison in your name, but using Edison Labs. Before we get into cables and a lot of what's happening, because you all, I know you've got some depth, and there is a lot happening throughout the entire power industry. Ben, take us through what you think some of the major changes that the power industry as a whole has gone through and is going through right now, because there's more change today than I've ever seen before in this industry. And I think we could all agree that change is. Talk a little bit about that, Ben.
Yeah, from my perspective, of course, there's been a lot of change, but one of the significant changes is the demand for power. That's something that if you go back 30 years ago, we didn't see the demand. And it's not just for any power. We're seeing the demand for, well, the traditional, reliable, safe, and affordable power, but even more importantly, resilient power. And I would say that's one of the biggest changes. It used to be that utilities would use average metrics to drive their actions. In fact, many still do. But what we're seeing is that those average metrics obfuscate, they hide the challenges that we're facing. And you think about, from a challenge standpoint, with a lot of the distributed energy, with the greater demand and the need for resilient power in our lives. We use power to cook, keep our homes cool, to, in some cases, drive our cars. certainly for AI functions and so forth, and huge demand for energy for data centers. And so we have this huge demand side response, but then we have aging infrastructure. We're operating with our grandfather's grid here, and this grid is not only aging, but it was built for a different era, and now even the average storm that comes through creates chaos with a lot of our networks, and of course that has a big overhead component. But we're going to be talking about cable systems. That's part of the solution, but we also have to be thinking about the total cost of ownership. And when we think about the total cost of ownership, we think about what does it cost to operate the grid, and then what's the challenge to maintain it over time. And I think this high reliance, we've got a population that is ever increasing on high risk areas and geography. We have 30% of the U.S. Living along the first county along the coast. We have more people moving into the wildland urban interface. So we have more people living in floodplains. We have higher risk, bigger demand, and aging infrastructure. That's not a good mix for resilience, right? So I really think one of the biggest challenges and the changes we need to make is we need to be thinking about total cost of ownership of assets, whether that be overhead assets like the old traditional wood poles and solutions to make those systems last longer. And it's really no different with cables. I think cables, we really need to be thinking about the total cost of ownership and how do we extend the life of these assets. We're going to make the investment so that these systems can last 50, 60, 100 years instead of the typical, what people used to claim, 20 to 30 years.
Right. Bob, so he said a lot. You can either drill down into what Ben said or just from your perspective, all of this change that we're talking about. He's talking about demand curve. I know Southern Company here in the South has gone from the last decade of basically less than 2% growth, and we're in a growth area in the South, to 8% annual growth. That's a lot of growth. Now, they just happened to open a new nuclear production facility here, so they did it to meet it. But many other people they don't have the infrastructure for that kind of growth. Talk a little bit about all of those challenges, Bob.
So the growth estimate that are going on these days that we are seeing for the company I work for, there is much more work coming than we had ever anticipated. And the other thing that Ben didn't mention is a lot of the people that built that old system, that have maintained and operated that system, are fast approaching retirement and are retiring out of the network. And we have a large basis of young people coming in that are trying to learn, but unfortunately, with the advent of computers, most of the engineers were going into computer science because that's where all the technology was. We are beginning to realize we're having a personnel shortage as well. But, on the cable side, that's even more because most of the young people are going into the power side are going in either to substations or to overhead transmission. The power cable business has been around for 140 years. Thomas Edison, he built the Pearl Street station in 1882 and provided power. Actually, it was DC power to 59 customers in lower Manhattan. Nowadays, the last statistic that I looked at, in 2023, 7.2 billion people have access worldwide to electric power. It's quite a bit, and only 750 million do not. In our whole world population, that's a small percentage. And in the background of all that, our benefits to the humans, the reliability of grid is taking on more and more of a prominence. Gone are the days when a power outage is tolerated by the public. They used to get, they understood that things break. Nowadays, they don't want to hear it. When voltages were a lot lower than what they are today, customer counts were lower, and the public would tolerate. Had a higher tolerance for outages they weren't happy. But nowadays, you couldn't work on things without de-energizing them in the past, because people would tolerate it. Nowadays, de-energizing a circuit for them, they're up in arms. And also, human safety was not as institutionalized in the past. In the old days, electricians would check a circuit, a low voltage circuit, by touching it with their hands, lick their finger out, and if it bit them, they knew it was still hot, and then they'd go try to figure it out. They were totally unaware of the risk to their life and limb. Today, we know better. Safety has become a priority above all else. We at Burns and McDonnell firmly believe that every worker, all workers, should go home at the end of the day in the same health and condition that they started their day with. There's no reason we're smart enough not to put them at risk at that. We as a company personally believe that, we don't have the right to ask a worker to be exposed to any risk that would jeopardize their health or life. And even OSHA training, when you go through that, talks about requiring personal protection equipment, PPE, when conditions require. It's interesting that OSHA states that the PPE should be a last resort if at all possible. And what they really state is that you should design all need for PPE out in the design phase. In the past, we didn't have that criteria. So I'd like to challenge all the engineers in the power industry, both young and old, to start taking a look. Can we design cable systems and the associated equipment to not require PPE? Those designs would help us help the new builds going forward. The tough question is, how do we improve what we currently have in the existing systems today? We have an opportunity with all the new growth, all the new reliability requirements and everything else to also design cable systems going forward to be a lot safer to work in, so we don't have to send people into manholes with energized cables. Got a lot of young, smart engineers joining the ranks and maintaining and building the new grid. We need to teach them the way we have always done this, and it's in the customer specification. May not be the best way going forward, and it's time for them to start taking a look what is better for the guys.
Excellent. Thank you, Bob. And by the way, there is a study. Ben and I are part of an organization called the Safety and Reliability Association. There is a study, and we're going to be working with some government grants to get this out there. That bite that you talked about, the electrician doing that? Electricians have a double the rate of suicide, double the rate of divorce, double the rate of PTSD than the population at large. So just like when your brain is not wired correctly, they might do electric shock. The alternative is true. When your brain is wired okay and you keep getting small voltage electric, so it's not sending you to the hospital, but you know what? It's not just work safe, home safe. It's home safe for a long time. But it's interesting that you talked about that, because we got to get the electricians to stop touching it like that, because it's not healthy. Dr. Wen, we're off on a tangent here, but go ahead.
Yes. So I like to talk about one topic that Bob mentioned. It's about the increase in power demand, which is a very important issue we all need to pay close attention to, especially today, because the increase in demand is very rapidly increased. Taking into consideration of not only increased number of electric vehicles, but also the increased use of AI and other computer-related programs, such as quantum computing, machine learning, and nowadays it seems all the companies are talking about taking the advantage of AI technology, machine learning, and then a lot of the universities are working on quantum computing. So with that, the demand of power, will stress our grid even further. So, for example, in Edison's underground network system, the increased power is a real issue for us because the increased power, as we all know, can increase the temperature, operation temperature, which on the one hand reduce the ampacity of the cable. On the other hand, the higher temperature will increase the probability of hazard, such as manhole events. So we need to deal with that, and we are working on the program. We call it the dynamic low release program. So traditionally, we have been working on our low release program based on static conditions, but now we are considering doing the low release program using the dynamic reason, taking into consideration of possible programs that can affect our load in over, let's say, 30-time period. So so we all need to keep in mind increase in power demand is a real issue for us.
Okay, excellent. So you just brought it down to what we're going to talk about now. Change in the industry affects every part of the industry. Load growth affects everything. We're going to talk about innovation and technology. It affects everything. By the way, I just found this out because I didn't understand why a data center that does AI has such high power needs. When you do a Google search on here or any, you use X power to do it. When you do that search and you take it through Chat GPT or you take it through Google Notebook or any of the AI functions, it's up to 1,000 times the amount of power. Now we know why they need as much power as they need. Not everybody can have a nuclear site like Microsoft did as their smart grid. Yes, Ben.
Well, yeah, and I'd like to tie that need and into a couple of points that Bob made, just to kind of close that this section of our discussion. You were mentioning, Bob, about the need to have good specifications. What we're finding in the research is that cable systems are failing, even age cable systems, most often, and I mean up to 90%. There are actual anomalies that existed from day one that are causing at least the initial fault. But then once you have a fault, at least for medium voltage systems, medium and high voltage systems, they're 10 times more likely to fail again once they've faulted once. So if we can bring the process back to the design, make sure that they're designed correctly, make sure that they're installed correctly, make sure that the manufacturing process is the quality it needs to be, and put in that design specification a commissioning assessment that actually can scan the line and find the defects before you energize. Now, not only are we getting rid of that first issue that can cause a safety issue, that can cause that exponential decay of the system, but we're also able to teach the folks that need to learn that they shouldn't have made the mistake to begin with, because the vast majority of problems are the installation problems, right? So the design, absolutely. And in fact, while we can't fix what's already there by design necessarily, we do have tools, and I'm sure we'll be talking more about diagnostics. And I know Yingli, you have a big experience with this, a significant experience with diagnostics. But that impacts the safety, reliability, and the longevity of these assets, which is, of course, what we're trying to do, is that total life cycle cost, trying to bring that down so that we actually can afford these reliable, resilient systems.
Yeah. So, Bob, go ahead, Bob.
So just on that note, one of the things that, from a reliability point of view, if the bulk of underground transmission in the United States has been high-pressure fluid-filled pipe-type cables, we are now shifting over from the high-pressure fluid-filled to solid dielectric designs. And in Europe, they've been using solid dielectric for a lot of years. And one of the things they learned early on was, and Dr. Wen mentioned this early, she was working on developing a cable that was less susceptible to the problems of water in the insulation, that could survive being wet. The interesting thing was, on a transmission side of the world, they have been designing what they call totally dry designs, both longitudinally and radially watertight designs. And the reliability of those cable systems has been phenomenal. Typically, the cables aren't failing. It could be any failures that are happening are typically traced back to workmanship in the splices. In the distribution world, we've been trying to design cable systems that can tolerate the water, but we have always known that water has been a problem for the cable insulation material. And it's a learning curve that has gone over and over again. And I find it interesting, Ben's comment that, if the cable suffers a fault, it's susceptible to more faults. It's been weakened. And, maybe that's why the transmission side has been having higher reliability when the distribution side hasn't. Now, there is a lot more distribution installed than there is overhead or underground transmission. However, I think we're going to be seeing a lot more of both going in the ground, just for all kinds of reasons.
Well, and I'd like to, I know that we probably need to move to the next section of our discussion, but I'd like to have a little bit of a counterpoint there. So water has been a major problem for the paper insulated systems. You just take a piece of paper and make it wet, and the fibers just fall apart. And we thought water was one of the predominant failure mechanisms of solid dielectric cable, plastic and rubber materials. And we made huge efforts in the industry to get rid of water. But what we found is that water by itself actually doesn't cause the problem. It's water with the existence of anomalies. You have to have an anomaly which draws the water molecule to that location to create a higher stress in one area, a higher density of moisture, and then have a dry part. So while moisture is still a part, it's not the predominant failure mechanism it used to be with the old paper cables. It's part of the story, but the biggest part of the story is if you didn't have the defect there to begin with, we wouldn't have to even worry about the water, at least for medium voltage. High voltage, sometimes there's some losses we need to worry about. But for medium voltage cable systems, we got rid of the manufacturing defects and the installation defects. We'd be a long way down the road, because we're looking at 90% of age systems. When you actually find defects that are on their way to failure, there's an existing anomaly that existed there from day one. So that's one of the big aha moments that I've had over the last 30 years. And I know that you've been taught by a lot of the same folks as I have. And water was like, well, you just got to get rid of it. And the reality is these days, there's even wet designs for at least medium voltage. So I'm not promoting putting moisture in a joint interface or something like that. The water and the cable, I think we are learning that it's not as big of a deal as it used to be. It's more about the workmanship and the anomalies that exist from the manufacturing and the installation.
Bob, I'm going to let you and Ben geek out, but I need to hear from Dr. Wen. So you hear the two of them talking about all of this, and let's just stay right now on that subject. Anything to add with what Ben said, what Bob has just said?
So about water in the extruded diagnostics, I agree with Ben. It's not really an issue unless you have other actors comes into play. And what I learned when I was working on my dissertation was that, for example, EPR cable, right? So if you have some EPR cable, if you have water get into the EPR insulation, and the water get through the distributed through the EPR wall evenly, it actually help the cable operate better, because now it instead of having stress concentration, now you have the electrical stress a little bit more evenly distributed, right, through the cable insulation wall, right? So, but being that said, with water in the insulation does increase the loss in the cable, which will, in the long run, especially in a large system, that loss equates to cost, right? So yes, I think so. We still need to try to keep water away from cable, and then in the case of XLP cable, now under electrical stress, and if you have contaminant in there, that will be the aluminate that Ben mentioned. Now you would develop water jet. So that can be an issue.
Okay, good. Bob, you're going to close this one out because I got another question for you. But go ahead.
It'll close this one. Is that the one thing that we didn't mention is the manufacturing process for polyethylene and EPR has greatly improved over the years. The cleanliness of the polyethylene is getting significantly better, and that is one of the major factors that brought along the elimination of impurities in the compound allowed for the large high voltage DC cables. They were trying to use the AC compound to be able to move up to the DC, and they hit a wall electrically because it wouldn't survive. So, Ben, you're absolutely right. The impurities have been a problem from day one. The water at early time frame helped make it go faster and cause bigger problems. And as we've gotten smarter and developed more, they're beginning to see, and actually they're doing wet designs at 66. I'm an old school guy. I don't trust it. But I do know the facts that if it's dry, you don't have a problem. So I'll say that much. Back to you, Alan.
So we usually wait until the end to ask questions, but we've got such a good question that is right about where we all are. So I'm going to ask it, and then raise your hand for whoever wants to take this one on. So what kind of testing and tools can be used during site testing to identify issues with cable systems without risking damage to the cable? Or, okay, Ben, you got this one. Or is there always a risk not always catching latent issues versus damaging of the cable when testing? Take that on.
Yeah. So there's two categories of cable. If we ignore the old paper insulated systems for the time being and talk about modern systems, plastic and rubber, we have low voltage systems and we have medium and high voltage systems, which really have two different failure mechanisms. Low voltage systems fail by a process where the material, the actual insulation is damaged. And even then, it doesn't necessarily fail because the ground, earth around it, or air is actually an okay insulator. And you can have leakages through the earth. And there's actually technologies that can scan across the earth. Even Con Ed uses it, scanning down their streets to find these leakages coming from cables that actually have breaks in the insulation. So there's technology on the low voltage side. There's also technology to detect if it's aluminum conductor, where there is a low voltage aluminum conductor where you actually get higher resistances, and you can detect it with meter reading. You actually detect a low voltage implication and identify issues that way. When it comes to medium voltage, the world changes. If you look at the history of cable, we won't go into that. But as soon as you get over 1,000 volts or so, really in particular 3 kV per millimeter, air is no longer a good dielectric. So if you have any air within that material, it's going to actually arc inside the air, and it's going to start deteriorating. And the manufacturers figured this out a long time ago. Since the 1960s, the manufacturers have used a power frequency, 50 or 60 hertz, partial discharge test to do all quality control of joints, terminations, and every reel of cable before it leaves the factory. And it's the gold standard of quality control in the factory. And in more recent years, we've actually figured out how to do it in the field. And provided we can actually achieve a similar sensitivity to the manufacturer, which is a 5 picocoulomb sensitivity, we can actually scan the line and find these little defects, which are going to cause failures months, years, even decades down the road. And that's really part of that design process, making sure we catch those issues from day one so they're not introduced into the system and have this intermittent erosion process that can fail it further on down the road. That's really the primary mode. There's still some people out there who are doing, say, insulation resistance tests and withstand tests, but those are typically less than a 1% solution compared to what we call what would be a factory comparable quality control check in the field, even for aged cables, which has a track record of being over 99.9% effective. Now, anytime you put a stress in the cable, there's a potential for a risk. Even testing cable systems online, it's still under stress. So anytime you have stress, you have potential for erosion, there's potential failure. So there's no such thing as no risk, but there are assessments that are less risk than others.
All right. So, Bob, you can either respond to that or we're going to move ahead, because what we did, you all went right into it. What all of the change that's taking place in the industry is affecting cables, is affecting cabling, is affecting your industry a great deal, some of which you've already talked about right now. But take a step back and just think about what we started with, change in the industry. Talk about the impact of that change on what's happening in the cable industry.
Well, a prime example was the training of the people in the field putting the cable systems together. In the days of paper-insulated lead-covered cables, which was primarily used up through probably the 80s, and I'd be willing to bet there's still a lot of it installed in New York, all over the country. And those cables are very reliable systems, but you could not make a splice in the field without at least 5 years, 1,500 hours of classroom, 5 years of apprentice work. And nowadays, with pre-molded accessories and kits that are provided as a complete package, the preparation and the training and schooling of those people that are assembling that is a lot less, to say the least. And because it's a lot less, there's more prone to failures due to workmanship. And with us but we need those types of accessories to be able to get in the field, get more people trained, and that's going to demand a better approach to being able to put cables together. There really is no good, clean method where you, like low voltage, you just take the insulation off, put a crimp connector, a little vinyl tape, and you're back in business. The high voltage, medium voltage, significantly more challenging, and craftsmanship, believe it or not, the craftsmanship is really critical when you're doing high voltage cables. If I was a school teacher teaching cable splicing, I'd start the guys out on high voltage cables, because what you can get away with on low voltage can't get away with on low medium voltage. You can't get away with on the higher voltages. And as you get up to, right now, today, a DC cable splicer needs 2 years of training before they'll let them do their own splice.
Yeah. And is that where a lot of the anomalies you're talking about come in, Ben? Is that?
Absolutely. Our studies have shown we have over almost 300,000 assessments in the field, line scans, as well as over 8,000 dissections that we've done. And over and over and over, it's like a 95% split. And it's like 90, it's almost precisely that. That's not just a swag of installation problems versus manufacturing problems. Manufacturing problems exist, but that 5%, when it does exist, it's usually systemic. It's all over. It's repetitive, but it's isolated to one reel of cable or a batch of terminations or joints. Whereas workmanship, 40% of new installs have at least one substandard component, meaning it didn't leave the factory that way. Somebody damaged it, and it's not meeting the minimum performance expectations. So 40% of our assets are getting installed with ticking time bombs that may take months, years, maybe even decades to go to failure. But remember, once you have the first failure, it's 10 times more likely to fail again.
Yeah. Dr. Nguyen, you see this in a practical way. Go ahead.
Yes. So, adding to Bob's point about the importance of the quality of spices, so we realize that is a very important aspect, and also we learn about that from real life experience. So we actually have an in-house spicing school, and spices has to go through don't call me, I think, months of training in the splicing school and take the final test, and they can go to the field and splice the actual cable only if they pass the test. And then over time, they also need to do splicing refresher course periodically. And on top of that, we also have a program like every newly made splice is tagged, and with all the information, the day it was installed, and what material was used, and even the name of the splicer. So if the splice fail within reasonably short time period, we will do a forensic analysis, and if it is deemed to be due to workmanship, then we will talk to the splicer and actually invite the splicer to the forensic session, and then the splicer would lead to recertified. So that tells you how important it is. And also another point Bob touched upon was about the a lot of the old cable, like PILC cable, are still operating very reliably as long as the lab chief is intact, which is the case for us. So we still, even though about 20 years ago started, we have a PILC replacement program, and which reduced the number of PILC sessions in our system dramatically, to the point that the remaining was so reliable, and we stopped the replacement program. But again, splicing those cable is not easy. You really need splicers who have that type of skill require to splice. So yeah, we has our splicers trained in that area. And again, earlier you touched upon about the knowledge transfer, right, with employees retiring and new employees coming in, and kind of some skill get lost. So we also have a program. We still have a lead wiping facility in our training school, and we'll train our splicers as needed.
Okay. Then you're going to take this next question, because we got a good question in here. Is there a difference in joint splicing hours in AC versus DC systems? If there is a difference, what is that difference?
Okay. Splicing hours. Could you clarify?
Training hours, you mean?
The second part of that question is training hours, but it's just the amount of time it takes to splice in an AC system versus the amount of time it takes to do a splice in a DC. That's what the first question was.
Yeah. Okay.
That might be a Bob question, right? Unless you know, Yingli, do you have experience with DC cables? I know Bob does.
I have to say no. And before move on to Bob, I'm going to say very quickly, we actually do not have DC system, or DC cable in our system anymore, especially the distribution at the distribution level, because the pure straight DC station that Bob mentioned earlier was retired. I believe was 15 years ago. So we retired our last DC operation system many years ago. So,
Bob, the DC splices, typically the DC splices that are being talked about today are 320 kV to 525 kV. And those are all done by the cable manufacturers. There are a few contractors that are learning how to do that. But just like with AC cable systems, the higher you go in voltage, the more critical the process, the cleanliness, all the operations are. And so to have that happen, you've got to go slower and better trained people. In distribution world, it's all AC. And there's a lot more going on. And as I said earlier, it's more voltage dependent than it is either AC or DC. However, the DC systems, there are some techniques and some proprietary information in the splicing process. That's why it all stays with the individual vendors. It has not become as widespread. Dr. Wen mentioned that currently they don't have DC, but in their network coming in, they have DC supplies coming in. There's one up at Cross Sound up in Long Island, and you've got a new project coming in. It's called the Champlain Hudson Project. It's bringing 400 kV DC from hydropower up in Canada into New York City. That's under construction. Those kind of systems you're going to be seeing more and more of. The New York ISO actually is looking at bringing DC circuits into Zone J, which is New York City area, from offshore wind. They're actually trying to bring in, I think, almost 4 to 5 gigawatts of power. So that's out on the street. So you may have retired your old stuff, but I think you got new stuff coming down the pike pretty soon. So the time frame wise, it's more voltage that takes longer. And, the other issue with very high reliability requirements, because you are moving in the Champlain Hudson project, 1,250 megawatts of power, that has a big effect on a network. So you want a very reliable system. Yeah. And so they are very careful about that.
Excellent.
I hope they answered that.
You all, we kind of had a flow of what we wanted to do, but you all keep answering the questions down the road that we were. And another one, I want to switch gears again. There is an enormous amount of innovation that is taking place, Dr. Wen, within the power systems. I mean, everything is going digital. We're going from electromechanical to digital systems. With all of that innovation that's taken, they're even innovating transformers in terms of production methodologies and materials and things. In the cable industry, talk a little bit about some of the major innovations that are either being put in place or that are coming.
Okay, so in terms of the cable system, right now we are focused on like existing cable design, but pay more attention to the manufacturing quality of the cable. So we work with the cable manufacturer very closely, and we have a periodic audit of the manufacturing facility to make sure they produce the cable to our specification, and also do the cable factory testing the way we required. So Con Edison's purchase specification actually is more stringent than the industrial specification, because we want to make sure the cable have like the best quality to start with, right? Like Ben said, if you have some defects in their contamination to start with, you're going to have problem down the road sooner or later. So we are mostly focused in that area in terms of cable technology. So in terms of design or material, we are not making much change in that area right now.
So Ben, let me ask you that. How do manufacturers create a better quality product that reduce all these built-in things? Are there innovations in manufacturing that they're using?
Yeah, well,
or is it just watch them closely? And there's got to be some way to be able to allow Con Ed to say, hey, that's a better cable.
Right. So both Yingli and Bob have experience in this, and of course I do as well. I mean, we've spent a long time in the lab looking at manufacturing defects that we identified in the field when we were doing some commissioning scans of new installed cable systems. And we actually created a co-authored paper that was presented at the Chicago conference in 2019 on this very subject. And we detailed all the types of defects, and then what are some of the things manufacturers can do. Now, we've come a long way from the days of the 1960s and 70s where when they extruded the material, they just had it open to the air, and anything, even flies or whatever, would get into the cable. We've come a long way from that, because now we know, as Yingli said, and Bob was mentioning earlier, that these little issues, especially as you go higher and higher voltage, make a big difference further on down the road. So we've got to the point where we know how to make the cable very well. And from time to time, there's manufacturing issues. The quality control testing. Sometimes we've had one manufacturer that ended up replacing like 3 of their testing bays because the equipment wasn't effective. Issues were getting out to the field. So there's a human element to this, right? It's more about the human element rather than the science. We know the science, we know the process, we know the materials, but is the human checking to make sure the equipment's working? Is the human checking the quality process to make sure that the quality process is functioning the way you expect? So as far as innovations with the quality, I think we've seen we're I think at a pretty stable point. And when there's anomalies, the industry works well together to solve those. I will say innovations with cable. Dr. Yingli Wen has experience with some superconducting cable. Bob has the experience with high voltage DC systems. These are, to me, where at the upper end of the capability or the extreme applications, we're starting to see some changes. But that technology is starting to drift down into lower voltage. For example, some of the solar and renewable sites, there's an interest in having medium voltage DC cables. So we got rid of DC, with the old Edison plants, the old Edison Westinghouse argument, AC versus DC. But now DC is starting to come back from, I would say, extreme designs to more regular designs, primarily because we have switching power supplies that can adjust voltage for us. We don't need the transformers like we did before. So I think that's where we're going to see a lot of innovation.
Bob, you had a comment on what Ben was talking about.
Yeah, and so the cleanliness, and I think there still is an awful lot of innovation going on in the manufacturing facilities. It's unfortunate that the general public and the general users of the stuff don't always see that, because somebody who makes a more reliable cable can claim better reliability in the marketplace, so it's a competitive issue. However, the whole industry as a whole has learned that, back to the inclusions in the compound, when you consider they're moving hundreds of thousands of tons of compound and extruding it onto the cable, and they're having to make sure that there is nothing anywhere in that system. It's a very demanding process that, in the high voltage cable manufacturing world, no human hand ever touches the compound. It comes from the factory in a sealed container. It goes into the extrusion line and gets put into that system in a sealed system. The cleanliness, or on the same cleanliness levels as some of the integrated circuit manufacturing facilities where they're working. In the old days, as Ben mentioned, they used to have what they called a 2+2 extrusion head, where they would extrude the inner semicon and the half of the insulation, and then it would have an air gap of 10, 15 inches, and another extrusion head would do the other half. And they wondered why they got flies and other stuff in the compound. And that will create havoc on the cable system and cause all kinds of problems. I think Dr. Wen's pushed for a higher than the industry standard. Those are minimum requirements. The industry standard is pushing higher and harder. And with that, the cable manufacturers are responding. They're doing continuous improvement. I don't see in any of the cable companies that they've slacked off on that continuous improvement, because there's a large dollar amount that can come back to bite them if there's a problem. So consequently, they're as keen on improving industry, better ways to sense, is there a problem? Better ways to test in the cable. On the transmission side, if a cable makes it out of the factory and past all the factory tests, the probability that cable, unless it's damaged during installation, is very low that you'll have a failure of the cable, except in the splices where humans touch it. And as Ben mentioned earlier, we humans tend to screw things up.
I think it's interesting that there's no human element in the making of the cable.
Oh, yes,
anymore,
there is.
but the human element is still the problem in the breaking of the system. Ben, we're coming close to the end. I want you to wrap it up. I want you to talk about just this whole idea. We're moving from a time-based maintenance philosophy because we know it doesn't work, and we're moving to a condition-based maintenance philosophy. Talk about that as it relates to cables, that you're able to use condition-based monitoring to be able to help people detect anomalies and solve it. So bring us home with that.
Sure. So online monitoring is really the holy grail of all of the testing approach. And there are some good online monitoring techniques for the low voltage cable. I've already mentioned that. And some good testing technology. With medium voltage, it's still, and in high voltage, it's still a work in progress. It's more of a research. We're starting to see some applications showing some promise, but it's still something we're learning. So one of the best approaches to date is to be able to scan those lines from day one, fix the issues that are there from day one. That would be 40% of the new installs having at least one issue. So 1% of cables, 4% of terminations, 4% of joints, fixing those, making sure that they're retested and they're meeting industry standards, making sure we have a good design like shear bolt connectors for the aluminum conductors, and bringing the neutrals across on the splices and putting good over voltage protection. Once we have the system installed properly and we don't abuse it through extreme voltage events or high extreme loading events or mechanical damage, really, unless you have chemical damage or irradiation, these systems are stable. So, but unless you have one of those events, those extreme events happening, there's really no reason to go touch that asset unless you had the event. Then you got to go back and rescan that line. And what we're finding is that even on 30 to 40-year-old cable systems, which are failing at an excessive rate, when you go and you scan those lines, it's only discrete defects, those little locations that get cut out. The rest of the material, from an electrical standpoint, is comparable to new cable from an electrical performance standpoint. So we're finding that these discrete anomalies, if we can remove them and protecting against extreme events, the assets can last a lot longer. In fact, some of the utilities these days are putting it into their rate cases that they're going to have these systems last 60 years or longer. Some people are saying 80 years or 100 years. So the recipe for good quality cable systems is actually becoming clear now with the data that we have. And if we can remove the defects and protect against extreme events, and if an event happens, go back to and baseline it, these assets are going to last a lot longer. And the total life cycle cost is what we're after, will be the lowest it can be.
You started with total cost of ownership.
I did.
And you're ending with total cost of ownership. Last comment, Bob, and when?
And I'd just like to add, you've heard us talk about all the problems with cables, but all in all, I would think everybody would agree, for the most part, cable systems worldwide are doing really well. We have a few problems, but the cable, all in all, most of the time you put it in the ground and it lasts for a lot longer than you were expecting. You get a good return on your money, and you have a very reliable system.
The data says 10 times more reliable than overhead. That's what the data's saying. So
Really? Underground is 10 times more reliable there? Wow. Dr. Yingli Wen, you get the last comment.
Thank you. So I want to say something about the online monitoring system. So we talk about all those issues with the system were like defects in the system and workmanship and all those, right? So we need to have a very reliable system that can monitor the power system and let us know when there is a problem or a problem is about to surface, and give us sufficient time to address it and remove the problem until it become a real problem, like causing an intended outage. So I also agree with Ben about online monitoring is maybe one of the best program to ensure the reliable operation of the power system. But I want to mention currently, even though a lot of companies have providing that solution, but in my opinion, a lot of these solutions are still in its infancy. We have a lot of issues to deal with, like how accurately the monitoring is, and how easily it can be installed. It's not easy for a very large underground network system like the one in Edison, in which the cable sections cannot really be isolated. They connected to each other. They permanently connected to transformers and network protector and other equipment. But anyway, other issues like cybersecurity, communication, and the list can go on. So we just need to keep that in mind.
We could, it sounds like we could keep going on and on and on, but we've come to the end of our time. There is an issue that we're doing later on in the year, and it is monitoring and diagnostics. Usually it's about transformers, but I want to include cables from now on, so we talk about those kinds of things. But this has been an APC Media Power Panel. Bob, thank you. Dr. Yingli Wen, thank you. Ben, as always, thank you.